Students, today let us discuss properties of inverse trigonometric functions. First property, sine inverse of 1 by x is equal to cosecant inverse x when x is less than or equal to -1 or x is greater than or equal to 1. This can also be written as x belongs to minus infinity to -1 union 1 to infinity. Okay, let me prove this result now. Proof. See, we have to show that sine inverse of 1 by x is equal to cosecant inverse x. I will start with the sine inverse of 1 by x. I will take that as y. Let sine inverse of 1 by x is equal to y. By definition, this will imply that sine y is equal to 1 by x. When the sine y is equal to 1 by x, we can write x is equal to cosecant y, because sin y equal to 1 by x will give you that x is equal to 1 by sin y. 1 by sin y, the reciprocal of sin y, which is cosecant y. So x is equal to cosecant y. By definition of cosecant inverse function, we can write y is equal to cosecant inverse x. Okay. Now we compare these two equations. Look at this equation. I'll call this as equation 1. Sine inverse of 1 by x is equal to y. And now you come to this equation. Y is equal to cosecant inverse x. I will take that as the second equation. From these two equations, from equations 1 and 2, we can write, say here, sine inverse of 1 by x is equal to y, and here we have y is equal to cosecant inverse x. From these two equations, we can write sine inverse of 1 by x is equal to cosecant inverse x. This result is valid only when x lies in the interval minus infinity to -1 union 1 to infinity. You might get a doubt, sir, why x is valid, why this result is valid only when x lies in this interval, why not in any other interval? That is because, as we know, the domain of cosecant inverse x. Cosecant inverse x is defined only when x lies in this interval. Therefore, this result holds good only when x is less than or equal to -1 or x is greater than or equal to +1. Okay. Now, let us go to the second property. Second property, that is cos inverse of 1 by x is equal to secant inverse x if x is less than or equal to -1 or x is greater than or equal to 1. Here also this can also be written as x belongs to minus infinity to -1 union 1 to infinity. Proof is very similar to the previous proof. Cos inverse of 1 by x, I will take that as 1. Let cos inverse of 1 by x is equal to y. Let this be equation 1. Now, by definition of cos inverse, we can write 1 by x is equal to cos 1. Cos inverse of 1 by x equal to y will imply that 1 by x is equal to cos y. If 1 by x is equal to cos y, then x will be equal to secant y, the reciprocal. Cos theta can also be written as 1 by secant theta. Cos theta and secant theta are the reciprocals of each other, as we know. So 1 by x equal to cos y will imply that x is equal to secant y. From x equal to secant y, this will give you that y is equal to secant inverse x. Y is equal to secant inverse x. So now I will treat this as equation 2. From equation 1 and equation 2. Look at these two equations. From 1 and 2, we can write cos inverse 1 by x is equal to secant inverse x. Whenever x belongs to minus infinity to minus 1, union 1 to infinity. This is the second property. Well, now let us go to the third property. Third property. Tan inverse of 1 by x, tan inverse of 1 by x is equal to cot inverse x whenever x is greater than 0. If x is greater than 0, then we can write tan inverse of 1 by x is equal to cot inverse x. Proof of this result, like what we did in the previous two cases, here also I'll start with let tan inverse of 1 by x is equal to y. This will imply that 1 by x is equal to tan y. By the definition of tan inverse function, we can write tan inverse of 1 by x equal to y will imply that 1 by x is equal to tan y. If 1 by x equal to tan y, then x is equal to 1 by x is equal to tan y, x, the reciprocal of tan y, which is equal to cot y. X equal to cot y will give you that cot inverse x is equal to y. X equal to cot y will imply that cot inverse x equal to 1 y. So here we have tan inverse of 1 by x equal to y, and here we have got cot inverse x is equal to y. Therefore, tan inverse of 1 by x is equal to cot inverse x whenever x is greater than 0. When x is less than 0, what happens? That we shall discuss in our next classes. Okay, so what we learned now is sine inverse of the, let us recall these three properties. Sine inverse of 1 by x is equal to cosecant inverse x if x is less than or equal to minus 1 or x greater than or equal to 1. Then the second property, cos inverse of 1 by x is equal to secant inverse x if x is less than or equal to minus 1 or x greater than or equal to 1. And the third property, we have learned that tan inverse of 1 by x is equal to cot inverse x if x is greater than 0. Okay, now let us move to our next set of properties. In the next set of properties, among them, the first one is sine inverse of minus x is equal to minus sine inverse x if x belongs to closed interval minus 1 to 1. Okay, let me prove this result. Sine inverse of minus x is equal to minus sine inverse x whenever x belongs to the closed interval minus 1 to 1. This result I have to prove now. I will take sine inverse of minus x is equal to y. Let sine inverse of minus x is equal to y. This will imply that sine y is equal to minus x. Sine inverse of minus x equal to y will imply that sine y is equal to minus x. Sin y equal to minus x. From there I can write x is equal to minus sin y. X can be written as minus sin y. That minus sin y I will write sin of minus y. Minus sin y can be replaced by sin of minus y because we know a property that is sine of minus theta is equal to minus sin theta. by using that property, I can write minus sine y as sine of minus y. This will imply, see here, we have x is equal to sine of minus y. Now, by definition of inverse trigonometric function, we can write minus y is equal to sine inverse of x. X equal to sine of minus y will imply minus y equal to sine inverse x, or y is equal to minus sine inverse x. Minus y equal to sine inverse x. Hence, y is equal to minus sine inverse x. Here we have sine inverse of minus x is equal to y, and in this equation we have y is equal to minus sine inverse x. From these two equations we can write that sine inverse of minus x is equal to minus sine inverse x. Sine inverse of minus x is equal to minus sine inverse x. Okay. Let us go to the second property now. Second property, that is tan inverse of minus x. Tan inverse of minus x is equal to minus tan inverse x for all x. X can be any real number. X belongs to R. Tan inverse of minus x is equal to minus tan inverse x. Let me prove this result now. Proof. So, let tan inverse of minus x is equal to y. Tan inverse of minus x is equal to y. This implies that tan y is equal to minus x. According to the definition, tan inverse of minus x equal to y will imply tan y is equal to minus x. So, this will give you x is equal to minus tan y. Tan y equal to minus x, therefore, x is equal to minus tan y. That minus tan y can also be written as tan of minus y. Minus tan y is equal to tan of minus y. Because tan of minus theta is equal to minus tan theta, which is a well-known formula. By using that formula, I am writing minus tan y is equal to tan of minus y. Okay, x is equal to tan of minus y we have. That will imply from this we can write minus y is equal to tan inverse x. Minus y is equal to tan inverse x. Therefore, y is equal to minus tan inverse x. Y is equal to minus tan inverse x. Students, we have started by writing tan inverse of minus x is equal to y, and we have ended up getting y is equal to minus tan inverse x. By looking at these two equations, we can write tan inverse of minus x is equal to minus tan inverse x. Tan inverse of minus x is equal to minus tan inverse x. This is true for any real value of x. X can be any real number. Okay, after this, let's go to the next result, which is cosecant inverse of minus x is equal to minus cosecant inverse x. Okay, third result now, cosecant inverse of minus x is equal to minus cosecant inverse x whenever x is greater than or equal to 1 or x is less than or equal to minus 1. Let me prove this result now. Proof is very similar to the previous two proofs. Let cosecant inverse of minus x is equal to y. Then by definition, cosecant y is equal to minus x. That will give you x is equal to minus cosecant y. x is equal to minus cosecant y. This minus cosecant y can also be written as cosecant of minus y, because I'll write here, since sine of minus theta equal to minus sine theta, this formula we know, and cosecant theta is the reciprocal of sine theta, so there we can write cosecant of minus theta is equal to minus cosecant theta. So x is equal to cosecant of minus y. This will imply that minus y is equal to cosecant inverse x. That will give you y is equal to minus cosecant inverse x. Here we have cosecant inverse of minus x is equal to y, and here we have y is equal to minus cosecant inverse x. By comparing these two equations, we can write cosecant inverse of minus x is equal to minus cosecant inverse x whenever x is less than or equal to minus 1 or x is greater than or equal to 1. Okay, say now you might be thinking, sir, you discussed only about sine inverse of minus x, tan inverse of minus x, and cosecant inverse of minus x. What happens to cos inverse of minus x, secant inverse of minus x, and cot inverse of minus x? That I am going to discuss now. So now I will discuss the next set of properties. In that, first one is cos inverse of minus x. Cos inverse of minus x is equal to pi minus cos inverse x whenever x belongs to closed interval minus 1 to 1. Say earlier I wrote a sine inverse of minus x is equal to minus sine inverse x, but cos inverse of minus x is not equal to minus cos inverse x. It is pi minus cos inverse x. Why it is so? Let us see now. Okay. Proof, as always, I will treat this as y. Let cos inverse of minus x is equal to y. It's not necessary that you must always choose this as y. You can take something else also. Say, if you are bored of looking at y, let me take theta. Let cos inverse of minus x is equal to theta. Then by definition, I can write cos theta is equal to minus x. That will give you x is equal to minus cos theta. You just compare the earlier proof, say in terms of, look at the first property, that sine inverse of minus x, we proved that it is equal to minus sine inverse x. There in that proof, we had x is equal to minus sine y, and there I wrote minus sine y as sine of minus y, right? Sine of minus sine y, I wrote it as sine of minus y. But now I can't do that, because here we have minus cos theta. Minus cos theta cannot be written as cos of minus theta. As we know, cos of minus theta is equal to cos theta and not minus cos theta. So I cannot write minus cos theta as cos of minus theta. Then what else can I do? What else can I do is, I can write minus cos theta as cos of pi minus theta. Cos of pi minus theta. X is equal to cos of pi minus theta. So from this I can write cos inverse x is equal to pi minus theta. Cos of pi minus theta, in other words cos 180 minus theta. Cos 180 minus theta is equal to minus cos theta. In the second quadrant, cos is negative. So cos 180 degree minus theta will be equal to minus cos theta. So I am writing minus cos theta as cos of pi minus theta, which will give you cos inverse x is equal to pi minus theta. From this equation, cos inverse x equal to pi minus theta, we can write theta is equal to pi minus cos inverse x. Theta is equal to pi minus cos inverse x. Look at this equation. Here I will treat this as equation 1 and this as equation 2. Cos inverse x equal to theta. Here we have theta is equal to pi minus cos inverse x. By comparing these two equations, we get cos inverse of minus x is equal to pi minus cos inverse x. This is true whenever x belongs to minus 1 to 1. Okay. Now some of you may get a doubt that, sir, why did you write minus cos theta as cos pi minus theta? Though it is true that cos of pi minus theta is equal to minus cos theta, therefore I wrote it in this way. But your question may be, sir, why not cos pi plus theta? See, if you look at cos pi plus theta, this is also equal to minus cos theta. Cos pi minus theta is also minus cos theta. Both are equal to minus cos theta only. Then also, why did I choose cos pi minus theta only? Why not cos pi plus theta? That doubt some of you may be having it. So I will clarify that doubt now. Okay. Say, if I write minus cos theta as cos pi plus theta, then what happens is x is equal to cos of pi plus theta. This would imply that pi plus theta is equal to cos inverse x. Then you may think, sir, theta is equal to cos inverse x minus pi. Whereas I got the answer as pi minus cos inverse x. You might think, what is wrong with this? Okay, what is wrong with this? I will explain. For that, let us go to the basic definition of cos inverse function. We write cos y is equal to x will imply y is equal to cos inverse x whenever x belongs to minus 1 to 1 and y belongs to 0 to pi. This 0 to pi, this is the principal branch of cos inverse x. Okay, so cos y is equal to x will imply y is equal to cos inverse x whenever x is in this interval and y is in this interval. So now we wrote cos inverse of minus x is equal to theta. This implies cos theta is equal to minus x. So cos inverse of minus x equal to theta means that theta will lie in this interval. Theta should belong to 0 to pi because that is the range. 0 to pi is the range of cos inverse x. So cos inverse of any value must lie in this interval. Okay. So theta lies in this interval. Theta belongs to closed interval 0 to pi. In other words, I can write theta is greater than or equal to 0, less than or equal to pi. Now, I want to know where does pi plus theta lie. So what I do is I will add pi to this inequality. If I add pi to this inequality, then we get pi less than or equal to pi plus theta less than or equal to 2 pi. So this pi plus theta now, that pi plus theta lies in between pi and 2 pi. Pi plus theta lies in between pi and 2 pi. Therefore, we cannot write this. Pi plus theta cannot be written as cos inverse x. This is not correct. You just recall the definition. X is equal to cos y will imply y is equal to cos inverse x. Whenever y lies in the interval 0 to pi, that angle should be in the interval 0 to pi. Now this pi plus theta is in between pi and 2 pi. Therefore, you cannot write this. Whereas, what I have taken, pi minus theta. Where does pi minus theta lie? That we shall discuss now. As we know, 0 is greater than or less than or equal to theta, less than or equal to pi. I want to know where is pi minus theta. So what I do is, I will multiply this inequality by a minus sign. When I multiply by any inequality by a negative quantity, inequality gets reversed. So you have 0 greater than or equal to minus theta, greater than or equal to minus pi. Or if you reverse it, I can write as minus pi less than or equal to minus theta less than or equal to 0. Now add pi to this inequality. Adding pi to this inequality will give you 0 less than or equal to pi minus theta less than or equal to pi. 0 less than or equal to pi minus theta less than or equal to pi, which means pi minus theta lies in between 0 and pi. So pi minus theta belongs to our desired interval, that is 0 to pi. Therefore x equal to cos of pi minus theta will imply that cos inverse x is equal to pi minus theta. Here pi plus theta does not lie in this interval, therefore we cannot write pi plus theta as cos inverse x. I hope you have understood. Okay, now let us go to our next property. The next property is secant inverse of minus x. Secant inverse of minus x is equal to pi minus secant inverse x. Secant inverse of minus x is equal to pi minus secant inverse x when x is less than or equal to minus 1 or when x is greater than or equal to 1. Let me prove this result. Let secant inverse of minus x is equal to y. This implies that minus x is equal to secant y or x is equal to minus secant y. X equal to minus secant y. Minus secant y can be written as secant pi minus y. Secant 180 degree minus theta is equal to minus secant theta. So minus secant y can be written as secant pi minus y. This will imply that pi minus y is equal to secant inverse x. Pi minus y is equal to secant inverse x from this equation. Here pi minus y is equal to secant inverse x. Take y to that side, bring secant inverse x to this side. We can write that y is equal to pi minus secant inverse x. So here we have secant inverse of minus x equal to y, and here we have y is equal to pi minus secant inverse x. From these two equations, I can write secant inverse of minus x is equal to pi minus secant inverse x whenever x belongs to minus infinity to minus 1 union 1 to infinity. This interval and this are one and the same. Okay. After that, let us look at the third result. Cot inverse of minus x. This is equal to pi minus cot inverse x. This is true for all real values of x. Let x be any real number. This is true. Cot inverse of minus x is equal to pi minus cot inverse x. Proof of this, as always, let cot inverse of minus x is equal to y. This will imply that minus x is equal to cot y. That is, x is equal to minus cot y, which will give you x equal to minus cot y is there. Minus cot y, I will write it as cot of pi minus y. Cot of pi minus y. Cot 180 degree minus theta is equal to minus cot theta. So I am writing minus cot y as cot of pi minus y. That will imply that pi minus y is equal to cot inverse x. Therefore, y is equal to pi minus cot inverse x. Bring cot inverse x to this side, take y to that side. we get pi minus cot inverse x is equal to y. Now compare these two equations. Here we have cot inverse of minus x is equal to y, and here we have y is equal to pi minus cot inverse x. By comparing these two equations, we get cot inverse of minus x is equal to pi minus cot inverse x for any real value of x. Let x be any real number. This is true. Okay, so we have studied some of the properties of inverse trigonometric functions in this video. In the next class, we shall discuss some more properties of inverse trigonometric functions before we go to problems. Thank you.